Work energy power. This is the next topic that we're doing now. Now, in the previous topics, forces, kinematics, Newton's second law of motion, most of the quantities that we talked about, they were vector quantities. Okay, now in this topic, work, energy, and power, all of these three quantities are scalar quantities. That means their directions do not matter, only their magnitudes matter. Now, work is the first one that we're talking about. It has a unit that's called joule. It's represented by this letter J. Work is defined as force in the direction of motion times the displacement. Okay, or W equals F times D. If you have a force acting like this, 25 Newton, and it's making an object move by 20 meters to the right, let's say, the work done by this is 500 joules. If it's acting at an angle, for example, this is 50 Newton, and the angle is 30 degrees, and the distance that the object travels because of that is 15 meters, you find the component of that force in that direction, and then you multiply that by the displacement. So 50 cos 30, that's the component of that force in this direction, times the displacement, that gives you the result. And that's what you get. Now, this can actually be generalized to something like this as well. W equals Ft cos theta. If you want to use that, you can do that. Otherwise, this resolving thing always works as well. But this is another formula that you could use for work when you have a force acting at an angle with the direction of motion. Fd cos theta, in this case, theta represents the angle between the force and the direction of motion. And if you just input the values of F and D directly in this and the value of theta, you would not have to think of resolving the forces in this case. But if you want to do it this way, by resolving forces, that's also fine. That will also give you the same value. Now, if you have something like this, that you have a force acting in this direction and the distance traveled is in this direction. In this case, if we were to find the work done by the force P, that would just be zero because force P does not have any component acting along the direction of motion. So that will just be zero. If you were to find the work done by the force Q, this is force Q, not angle theta, this is force Q. If this was 30 Newton, that would just be all of this will be worked by the force Q. That will be 750 joules. Now, if you have a situation like this in which there's also friction, so you have a force acting in this direction at an angle of 60 degrees, and there's friction that's opposing the motion of 15 Newton. In this case, one thing that you may have to find would be the work done by the force P. Now, when you find work done by a particular force, you just use that force in the formula directly. So 45, what's the component of that? 45 cos 60. Multiply that by displacement, that's 40, and that's 900 joules. You do not subtract friction from that. The work done by that force P would just be 900 joules directly. We are not going to subtract friction from that. If we had to find, I'll talk about that in a minute again. If we had to find work done against friction, what would that be? We would multiply friction by the force, by the distance traveled, that is 40 meters, and that turns out to be 600 joules. That's this value. Now, why did we not subtract this 600 joules from that 900 joules when we talked about work done by P? This work done by P, that's actually doing two things. The total work done 900 joules. Number one, it's working against friction. So this is the work done by P against friction. So out of that 900, 600 is being used against friction. And the remaining then, 900 minus 600, which is 300 joules, that is being transferred to the object as its energy. And that is what is going to make the object move to the right side. Okay, so the total work done by P, that is simply calculated using the formula directly. That turns out to be 45. 900 joules, but then some of it is used against friction, some of it is transferred as energy to the object. Yes, you could call it that. You could call it that. Okay, now, what if you have something like this, vertical motion? In this case, what's the work done by the force P? If you have a force P acting like this, 750 Newton, and because of that force, the object is moving 25 meters in the upward direction, you just multiply those two, and the work done turns out to be 18,750 joules. Work done against resistance. What's that? We have a resistance of 100 Newton. The displacement opposite of that is 25. We just multiply those two numbers, and that gives us work done against resistance. That's 2,500 joules. Work done against the weight. So we have this force acting in the upwards direction. It's also doing some work against the weight because weight is opposing that force. Weight is opposing the motion. Now, how much is that? Just multiply weight by the distance traveled, and that turns out to be 7,500 joules. Now, in this case, what's happening is the total work done by P is 18,750 joules. Some of it is being used against resistance, some of it is being used against weight, and the rest of it is transferred to the object as the energy of the object. Okay? Yes, so this total work done includes work done against resistance, against weight, and this. Okay? Next, we've got energy. So this energy that we talked about, now in our syllabus, there are only two types of energy. There are many different types of energy, actually, but in our syllabus, there are only two. And they are kinetic energy and potential energy. For any other energy, we will assume that that's negligible and we would not be considering that. Now, what's energy? Energy is also a scalar quantity. Its unit is also joules. There are two types of energy that we'll be talking about. One is kinetic energy and the other is gravitational potential energy. Kinetic energy is defined by this half into mv squared. It's mainly because of the speed of the object, right? That's the differentiating factor in kinetic energy. It is because of the speed of an object. Of course, mass plays a part as well, but mass is going to be in the other types of energy as well. But the speed is the distinctive part of this. Kinetic energy is because of speed of an object. It's defined as half mv squared. Gravitational potential energy, it's because of height of an object, and it's defined as mgh, where g is 10 and h is the height above the ground level. Now, mostly you'll be dealing with, you'll have to find out the difference, the change in kinetic energy and the change in potential energy. How do you find that? Let's say you've got a particle like this, an object like this, a block like this, and it's moving in the upward direction. And we know that it started from 2 meters per second and it reached a speed of 0.5 meters per second. And it traveled a distance of 30 meters in the upward direction. If we have to find the change in kinetic energy, we can think of it like this. Change in kinetic energy, what would that be? The final kinetic energy, we can say half mv squared minus the initial kinetic energy, half mu squared, where v is the final speed and u is the initial speed. We can come up with a formula like this from that. Half into m into v square minus u square. You can subtract them separately as well if you want, but this is slightly more efficient in questions. When you want to find change in kinetic energy, you can just say half into m into, you take half m common from this, right? And that leaves you with v square minus u square inside. That's the change in kinetic energy. What about change in potential energy? Now, in this case, potential energy at this point would be mgh1. At the other point, it will be mgh2. But we do not know the values of h2 and h1. How do you find change in potential energy then? We could say it's mgh2 into mgh1. Mgh2 minus mgh1. Take mg common, and that leaves us with h2 minus h1, the difference between the heights. So the change in potential energy is actually given by this mg into delta h, change in height. So whatever is the change in height, that's what we use in the formula right here. That's 30 meters, and that will give you the change in height. So again, mostly we will just be dealing with the changes in potential energy rather than absolute values of potential energy, rather than actual values of energy, especially for potential energy. In kinetic energy, sometimes we do find the absolute values. In potential energies, we mostly talk about the change. Okay, so in this case, the potential energy, for example, is going to be 5 into 10 into 30. Change in potential energy, and the change in kinetic energy is going to be this, half into 5 into 0.5 squared minus 2 squared, and that gives you this. When it's a negative value, that means the change is negative. The kinetic energy is decreasing. When the change is positive, that means the energy is increasing. Okay, so when the change is positive, that means it's an increase. When it's negative, that means it's a decrease. If you know that it's a decrease, make sure that you have a negative sign there. If you know it's an increase, you have a positive sign there. Now, we talked about how the work done by something is used for multiple things. Some of it is used against resistance, some of it is used against some other thing, and then the rest of it is transferred to the object as its energy. This is something that connects work and energy. It's called the work energy principle. You'll be using this a lot in this topic, work done by the driving force, that is equal to the change in kinetic energy plus the change in potential energy plus the work done against resistance. So the work done by a driving force is used against resistance, and the rest of it is transferred to the object as its energy. In short, we can write it like this: work done by driving force, that equals change in kinetic energy plus the change in potential energy plus the work done against resistance. Now, what is a driving force and what is a resistive force? Now, we've talked about forward forces and backward forces earlier in Newton's laws of motion. When we use F equals ma there, we say forward force minus the backward force. That equals mass into acceleration. Now, in forward forces, we've got all the forces that are acting in the direction of motion. In the backward force, we've got all forces that are opposing the motion, that are acting opposite of the direction of motion. So forward force and backward force, they just mean all forces acting in the direction of motion and opposite direction of motion, respectively. Driving force and resistance that we will mostly be using in this topic, this driving force and this resistance, their definitions are slightly different. They're not the same as forward force and backward force. Driving force is any forward force except weight. Weight is not considered a part of driving force. Except weight or any of its component, we will not include that as driving force. Resistance as well, it will be any force opposing motion, so that means all backward forces, except weight. We will not be considering weight as as a resistive force. Okay, weight is not going to be considered here. The work done by the weight or the work done against the weight is actually already incorporated in the change in potential energy. Remember what this is? mg into delta h. That's what potential energy is. Mg into delta h. Mg is weight. Weight into change in displacement. Weight into displacement. That's the work done by the weight or the work done against the weight. That is already incorporated in change in potential energy. If we also include that in driving force and resistance here, that will be double counting. So we don't include that here. Okay. So driving force does not include weight, and resistive force does not include weight. We use this in all cases, but just remember, in driving force, we will not include weight. In resistance, we will not include weight. So we can use this for horizontal surfaces, inclined surfaces, any surfaces, curved surfaces. This always works, this work energy principle. Just remember that weight is not going to be considered as part of driving force or resistive force. Okay. Then you have conservation of energy. It's actually a special case of this work energy principle. This will work everywhere. There's a special case for this, and that is when there is no driving force and no resistance. So sometimes what happens is there's zero driving force and there's zero resistance. Okay, there's zero driving force and there's zero resistance. So driving force is zero and resistance is zero. In that case, in this work energy principle, what happens is this value becomes zero, this value becomes zero. That means the total change in kinetic and potential energy, that turns out to be zero. The total change is zero. If the overall change is zero, that means whatever was the initial sum of kinetic and potential energies, that's going to be the same as the final sum of kinetic and potential energies. Okay. That's called conservation of energy. When there are no external forces, when there's no driving force and there's no resistance, when both of these conditions are met, in that case, we can say the total energy of the object remains conserved at any point in the journey. If you were to find the total energy, kinetic energy plus potential energy, their sum will always be equal to each other. Okay, so this is what happens. Not necessarily that loss in kinetic energy is equal to gain in potential energy or something, because sometimes you have both happening at the same time. So you, at some point, you might have both kinetic and potential energy. So this is a more general form for that. At every single point, when you add these two things up, they should be the same, right? That's the general rule. When There is no driving force and there's no resistance. Now, this is optional. If you want to use this, you can use it. Otherwise, everything can be done using the work energy principle as well, because that's just coming from this general equation. You could also just write this as zero, and then just find change in kinetic energy here, change in potential energy here, input their values, and you can find any unknowns that you have to. That'll work in every case as well. This is just going to work when there's no driving force and there's no resistance force. In that case, you can use this conservation of energy as well. Now, the next thing is power. Power is also a scalar quantity. Its unit is watt. Okay. Power is defined as the rate of work done. And one formula for that is power equals work done over time. In short form, we can say that's power equals P equals W over T. And that can then be converted to a form like this as well. Power equals driving force into velocity. These are the two power formulas that we've got. Power equals work done over time, and power equals driving force into velocity. Okay. Now, mostly we will be using this formula, driving force into velocity. In some cases, when you have time given or you have to find the time somewhere and you have power involved, in only those few cases, you will have to use this first equation as well. You need to know both of them, of course, but mostly you will see that the second formula is going to be used here. Okay, W is work done, right? So W can be written as F times D, force into displacement. So that gives us this. So this is one equation, and this is another. This is another formula. These are two formulas that we've got for power. You need to remember them. None of these formulas are given in the formula sheet. You need to remember them. Okay. Now, a lot of times you will see that you will be using these two formulas together in this topic. Power equals driving force into velocity, and resultant force equals mass into acceleration. For example, if we have a situation like this, we have an inclined surface and we have this block and it has some forces acting on this. There's a driving force acting in this direction. There's a friction acting in this direction. There's just normal reaction here. We've got weight components acting. All of these are there. And we have some power given. And we have to find something missing in the data. Maybe driving force might be missing. We might have to find acceleration. We would often be using these two formulas together. Power equals driving force into velocity, and resultant force equals mass into acceleration. Why? Because they're connected by this driving force that's common between them. So we can connect them using the driving force. When we write down the equation for the Newton's second law of motion, we would have a driving force minus the backward forces equals mass into acceleration. And this is going to connect these two things then, these two formulas. So these will be used together a lot. Just keep that in mind. These two formulas are used together a lot in this topic. Okay, let's move on. Now, in some questions, you will see, they will tell you that the acceleration at a particular point is maximum or minimum. Speed or velocity at some point, velocity or speed at some point is maximum or minimum. Now think about the velocity time graph. It would look something like this, right? When you have a maximum value, that means the gradient at that point is going to be 0. So whenever you have maximum speed or velocity, what that means is they're basically telling you that acceleration value is going to be 0 in that case. So when you use Newton's second law of motion there, you would say resultant force equals mass into acceleration. That means if acceleration is 0, then resultant force is going to be 0. That means the forward forces minus the backward forces, they should equal 0. And that gives us the forward force is equal to the backward forces. In this case, when acceleration is 0, forward forces and backward forces are going to be equal to each other. Okay. The other cases when acceleration is 0 are when velocity is constant, or so they could say it's constant velocity, constant speed, or they could say it's steady speed or steady velocity. In that case as well, acceleration is going to be 0. And this is going to hold true there as well. Forward force is equal to backward force. It could be true at rest. And also, as we talked about, maximum speed, because that's the turning point of this graph. At that point as well, acceleration is 0. In all of these three cases, remember, resultant force is equal to 0, or you can say the forward forces and the backward forces are going to be equal to each other. It's not always going to be that driving force is equal to resistance, because we could have some other forces as well. For example, in this situation, if it was constant velocity, you would say driving force equals friction plus W sine theta, right? Forward forces equal the backward forces. It's not always just driving force equal to resistance. It's all forward forces equal to all backward forces. All right. Okay. Let's have a look at some questions now. That's all that you got in terms of the basic concepts in this topic. But now in questions, you will see some more complications coming up. Let's say we've got this example. It's a fairly straightforward one. First up, we've got mass of a crate, that is crate of mass 50 kilograms. And we are given that it's moving on a horizontal surface by a force of magnitude 400 Newton acting at an angle alpha from the horizontal. So you can see that here, there's a force acting here. Because of that force, the object is moving to the right side. And it's moving a distance of 20 meters. So it's moving a distance of 20 meters because of this. There's a resistance of 250 Newton that is opposing the motion that acts in this direction, 250 Newton. First of all, what's the increase in kinetic energy? Just use the change in kinetic energy formula. Work done against resistance, how do you find that? You've got the resistance value, that's 250, times the displacement, that's 20, and that gives you the work done against resistance. Now, whenever they talk about work done against resistance, and you can figure out that they're talking about speeds, they're talking about the height changing somewhere, that's a clear indication for you that you would be using work energy principle. Especially this thing, work done against resistance, in almost all questions that involve this, because of this being there in this equation, you'll be using this work energy principle. So they are saying now in the third part, find the value for alpha. So now we have already got the change in kinetic energy. We've gotten the work done against resistance. We know there's no change in potential energy because the height is not changing. That's going to be 0. Using all of this, we could say, let's input those values in this work energy principle. Change in kinetic energy, that's 100. Change in potential energy, 0. Work done against resistance, 5,000. Work done by the driving force, what would that be? We had that force given. That force was 400 Newton. 400 into cos of alpha, that's the component of force acting in that direction, times 20, that's the work done by driving force. And just solve that, find the value of alpha from that. So this equation will be used a lot in this topic. Let's have a look at another example. We've got this car of mass 1200 kilograms that is traveling along a straight horizontal road. We've got the power of the car given, that's 20 kilowatt. Be careful about this unit. A lot of times they give power in kilowatts. That means it's 20,000 watt. In the formulas, you will always input the standard unit, that's watt. You will convert it to watts first of all, and then input that value in the formula. The resistance to the car's motion is constant, and it's equal to 500 Newton. The car passes through the points A and B with these speeds. Find the acceleration of the car at A. Now, how do you find that? Power is constant. The resistance is also constant. Do we know anything about driving force? Is the driving force constant? We don't know that. So we cannot assume that we can use constant acceleration formulas here. In work, energy, power questions, avoid using constant acceleration formulas. Avoid using equations of motion. You can use this, of course. This works every time. But the constant acceleration formulas, they will very rarely work in work, energy, power questions. So as long as you can find a way to do it using work energy methods, prefer that. That's going to be easier as well. Use work energy methods. You can only use constant acceleration formulas if you are sure from the question statement that all forces are constant. In that case, yes, you can say that acceleration is constant, so you can use those formulas. Otherwise, avoid them. You want to find the acceleration of the car at A. How do you do that? You've got power given, and you've got the speed given at the point A. That's 10. Using that, you can find the value of driving force. And then use Newton's second law of motion. to find the value of acceleration. That gives you this value. And then it says, by considering work and energy, find the distance AB. Now we've already found, we already know the value for the driving force. That's 2000 Newton. Using that, we can find the work done by the driving force, because the distance is 30. The distance is what? No, okay. So we do not use that because the distance is not given. We have time given instead. That's 30.5 seconds. If we have time given, we can use the other power formula to find the work done, because power is given, time is given, and that gives us the work done by the driving force. That turns out to be this. And then change in kinetic energy plus the change in potential energy plus work done against resistance. That will be 500. That's the force times the displacement, and that's what you have to figure out. Let's call that D. Simplify that, and you get a result from that. Okay. Now, something just came to my mind, but I'm forgetting now. Work done against resistance. There was a small point that I wanted to mention here. Yeah. So a lot of times you end up confusing resistance with work done against resistance. Please make sure that you don't do that. The resistance here is a force. This is 500 Newton. In the formula here, this is work done against resistance. Do not just input 500 here. It's supposed to be the work done against resistance. So 500 times the displacement, and that will give you the result. Okay. Let's have a look at this now. It says a cyclist and his machine have a total mass of 80 kilograms. The cyclist starts from rest and then he freewheels. Okay, so that was the important thing that I wanted to mention for this question. When they say there's a cyclist and that's freewheeling, he or she is freewheeling, that means there is no driving force. Driving force is 0. In this case, they've explained that here as well. Without pedaling or braking, what does that mean? There is no driving force. There's no driving force in this case. So there's no driving force. Just keep that in mind. And the rest of it, you can do it relatively easily. I'll just show this working for you. You can have a look at this in your own time. It's just the use of that work energy principle multiple times. Okay. All right. Yes, that's also fine. Work done. But how do you find work done here? Because work done against resistance is also unknown. So you can't find the work done by the driving force unless you've got this value here as well. It'll be in terms of D. So then you'll have to make that equation in terms of D and then input that there. That's possible. That will also work, but it might be slightly more lengthy, but that's possible. Yes, you can do that. A smooth slide AB is fixed so that its highest point A is 3 meters above horizontal floor. Now, whenever you have a curved surface like this, never use constant acceleration formulas here, because direction is changing at every single point. So the acceleration can never remain constant. Now, in such problems, a lot of times, you can use conservation of energy. Why? Because in many cases, this will be a smooth surface. Not always. Sometimes it can be rough as well. In that case, you'll have to use the work energy principle. Work done by driving force that equals change in kinetic energy plus change in potential energy plus work done against resistance. In general, you would use that. But when it's a smooth surface and there are no forces acting externally, no driving force, no resistance, you can also use conservation of energy. And that's the case in this case. There's no driving force, there's no resistance. So you can use conservation of energy here. So they're saying P is released at the point A. It's released from rest. Now, we have to find the value for H such that the kinetic energy of P at B is 1.62. So all we do is find the total energy at the point A, find the total energy at the point B, kinetic plus potential, equate them. Since the energy is conserved here, there's no driving force, there's no resistance. So energy is conserved at every single point of this journey. the total energy is going to be the same, right? So we use that to find the value of H there. Then it says kinetic energy of the particle immediately before it reaches the ground. So at this point, what's the kinetic energy? Again, use conservation of energy, and that will give the result. You can do that. And then they want you to find the ratio Vg to Vb. Now, sometimes they ask you for ratios like this. How do you deal with this? You'll find the Vg value, you'll find the Vb value, and just find their ratio by writing them as a fraction. So in this case, what's Vg? Vg is the velocity at this point. Vb is the velocity at this point. Now, again, you can say the total energy at every single point should be the same. So whatever is the total energy at the point B, and the total energy at the point A, and the total energy at the point G, they should all be the same. So we can make equations like this. Kinetic energy at, in fact, in this case, we had already found the kinetic energy earlier. Yes, that's actually done in the previous part. We have found the kinetic energy at the point G. Using that kinetic energy at the point G and the kinetic energy at the point B, we already know the kinetic energies both of those points. So we can find their velocities corresponding to them and find their ratio like this. So when they ask you for ratio, what you do is you find these two values separately and then provide them as a fraction like this, and then simplify that, whatever it comes to. That's going to be written in ratio form like this. So when they ask you for ratio, you find those values, write them in fraction form, and then you write them in ratio form like this. How do you know that energy is conserved? Because there's no driving force. The particle is released from here. There's no forward force that's acting. There's no driving force, and there's no resistance because it's smooth. It's a smooth slide. There's no friction. There's no resistance. So when you have both of these conditions met, no driving force, no resistance, that means that the energy is conserved. Now, in the case that P is released from the point X, what happens in this case? Now they're saying it's released from rest at this point. It's a separate case. Whatever we found in the previous part, that's no longer relevant, except, of course, the height of H. That's not going to change. If the height is 2.2, that remains 2.2. But now the particle is released from the point X, from rest. We need to figure out the value of capital H to two significant figures. Now, for this, again, we use conservation of energy. We say energy at this point, energy at this point, energy at this point, they are all going to be the same. So we make three equations from this like this. We say the total energy at X, total energy at B, total energy at G, they should all be the same. And from this, we can break it down into two parts like this. We get three equations. One was given in the question already, Vg over Vb, that was 2.55. And then the other two, we end up having to solve three simultaneous equations. We will eliminate the variables that we do not need and find the value of capital H from this. So sometimes this algebra can sometimes be a bit more complicated. You have three unknowns and you have three equations. The value that you're looking for is capital H. You try to eliminate the other variables from the other two equations and then just find the value for H like this, okay? So in this case, if you were to use work energy principle, that will make things more complicated because that will be a more complicated equation, right? So once you understand that there is no change in, there's no driving force and there's no resistance, in that case, it's easier to use conservation of energy directly. In this case, it's much easier this way. The question says it's released from rest. So let me find that again. Okay, yeah. So the particle is released from rest at a point on the slide. Okay. So in the first case, it's released at A. So it's released from rest at A. And the second case as well, it's released from rest at this point. Okay, so it's given in the question. All right, let's move on. So we just use conservation of energy. We equate all of them and we get the result from them. We solve these equations simultaneously. You can have a look at this working. It's just algebra. That's how it works. Let's have a look at this example. Now, sometimes you have inclined surfaces. Sometimes you have inclined surfaces. Okay, let me come back to that at the end. At the end, you can ask me any specific question that you have there. The car comes to, so there's a car that comes to the bottom of a straight hill that has the length of 316 meters. So you can have inclined surfaces like this as well in work energy problems. In this case, what you're given is that this length is 316 meters. And the angle that this plane, this surface makes with the horizontal is theta. I'm calling that theta. The angle is given to be sine inverse of 160. So that means theta is equal to sine inverse of 160, which implies that sine of theta, that is equal to 1 over 60. Okay, so that's the value that we're given. We're given the work done against resistance. We're given power that remains constant at 16,000 watt. Resistance is no longer constant. So in the previous parts, the resistance was constant in this question, but in this case, they're saying resistance is not constant. If it's not constant, it's a clear indication that you cannot use constant acceleration formulas here. The time taken is given to ascend the hill, to go from the bottom to the top. The car is traveling at 20 meters per second at the bottom, and we have to find the speed at the top. Now, it's a classic case of work energy principle. You've got power given, you've got work done against resistance given, you've got the this hypotenuse given of this triangle. You have the speeds given. You can find the height somehow, and you can use concept of work energy principle. Work energy principle looks like this: work done by the driving force that equals change in kinetic energy, and so on. What's the work done by driving force going to be? We've got the power value given, that's 16,000 watt. We've got the time given. Since we have time given, we use this formula to find the value of work done, and that turns out to be 240,000. We input that value here. Change in kinetic energy, what would that be? If we consider the final velocity as v, the change in kinetic energy, that's going to be half into m. Mass of the car was given as 1200 kilograms. 1200 into v square minus 20 square, that gives the change in kinetic energy. Potential energy, for that, you'll have to find that change in height. How do you do that? You can make a right-angle triangle like this. You're given the hypotenuse, that's 316. You know the angle, that's theta. Find the value for h. And from that, you can find the change in potential energy. Plus the work done against resistance, that's this. And that will give you the value for v that we were looking for. That's 6 marks, fairly straightforward. Just a simple application of work energy principle like this. Okay? Sometimes it can become more complicated. So you have multiple objects like this. You've got a car and a trailer. They're connected like this by a string. And you've got some forces acting on them like this. In the first part, they say F is equal to 100. Find the acceleration and the tension in the tow bar. How do you do that? Represent all the forces acting on both of them, like we normally do in Newton's second law of motion. Tension, there's no resistance here. Okay, so resistance is given. Resistance is given. We don't have to consider friction separately. When they give resistance, that includes friction anyway. So that means we can ignore normal reactions because they are only going to be required when you have friction involved. So we can just ignore them for that reason. Represent all the forces, apply Newton's second law of motion, both of them separately, and then find the values of T and A. That's really straightforward. That's Newton's second law of motion. Do not forget the weight components. A lot of times people end up forgetting the weight components. There are going to be weight components acting in this direction as well. You have to consider them. In Newton's second law of motion, you do consider weight. But then in the second part, it says it's given instead that the total work done against F in moving a distance of 50 meters up the road is 6,000 joules. So we know there's a force, there's a friction acting in this direction, and its value is given. Resistance acting in this direction, its value is given as F. Work done against that resistance, what is that? That is 6,000 joules. Again, work done against resistance. Does that remind you of something? Again, work energy principle. And they're specifying here as well, whenever they say use an energy method, that means this equation. Okay. The speed of the car at the start is given, that's 50 meter, that's 20 meter per second. And this journey is of 50 meters. How do you find the speed of the car at the end of the 50 meters? Now, notice the car and the trailer, they're connected to each other. So whatever is the speed of one is going to be the same speed for the other as well, because they're connected to each other. They've given the speed of car, the speed of the trailer is going to be the same as well. Now, to find the energy here, you can see both of them are moving in the same plane. So whatever is the change in height for one, it's going to be the same for the other as well. And whatever is the speed for one, it's going to be the same for the other as well. So we can consider this thing as one whole system. Rather than calculating them separately, you can calculate them separately as well, that's possible. But you could just consider it as one whole system and just do the calculations together for them. How do you do that? Work done by the driving force. What's the work done by driving force? We are given the work done against resistance. Did we have any value here? Okay, so driving force was given here. That's 3,000 Newton. That was given in the beginning. That is 3,000. That's still 3,000 here. You're traveling a distance of 50 meters. So 3,000 times the displacement, that's the work done by the driving force. Change in kinetic energy. Now, for change in kinetic energy, you consider the total mass of the car and the mass of the trailer. The total mass turns out to be 2,100 kilograms. So in this formula now, you can directly just input half into 2,100 into v squared, that's the final speed, minus u squared, which is 20 squared here. And that gives you the change in kinetic energy. You can also do them separately, but that will just make it longer, but that's also possible. You can do that. Similarly, for potential energy, you find the change in height. How do you do that? Making this right angle triangle. The hypotenuse is 50. What's the height going to be? You can find that using sine. And that gives you the change in potential energy. And then work done against resistance. What's the work done against resistance going to be? They have given us the work done against the force F. We do not need to find F here. I'll just remove that from here. We are already given the work done against the resistance. That's 6,000 for the trailer. But for the car, it's not given. On the car, there is another resistance acting, and that is 800 Newton in the backward direction. So for that, you have to find the work done against resistance separately now, because they only gave it for the trailer. They did not give it for the car. So for the trailer, it's 6,000. For the car, it's 800 times 50. And then you just solve this equation, find the value of V like this, and that gives you the result. So you can have multiple objects like this sometimes. You can consider that whole thing as a single system if they are both on the same plane like this. But then sometimes okay, just a couple of examples. Sometimes they talk about vertical distance, just like we did one example earlier in Newton's second law of motion. Let's consider this now. It's given that this plane is rough, so we have this plane, and we have the particles are in limiting equilibrium. In the first part, they ask us to find the coefficient of friction between V and the plane. We just represent all the forces, equate the opposite forces, and that gives us the coefficient of friction. That's pretty straightforward. The first part, 6 marks, easy 6 marks, the first part. But then it says, now what's happening is, it's given instead that the plane is smooth. And the particles are released from rest. The particles are released from rest. When the difference in the vertical heights of the particles is 1 meter. So initially, at this point, A is here, B is here. The difference between their vertical heights, that is 1 meter. And they are saying, use an energy method to find the speed of the particles at the instant when the particles are at the same horizontal level. Now, how will they be at the same horizontal level? A will move downwards in this direction by some distance, and B will move up the plane by some distance. Now, we don't know how much distance they're traveling, but they're connected to each other. If this distance is x, this is also going to be x, right? But then, since we want to use the energy method, we have change in potential energy here. For change in potential energy, we need to figure out exactly how much is A moving down vertically and exactly how much is B moving up vertically. That's the key part here. The rest is pretty straightforward because we've got the speeds given. We can find the change in kinetic energy from that. We've got the value for resistance given as well. I think we'll have a look at that. In fact, there's no resistance. It's a smooth surface. There is no resistance, so that's just going to be 0. So the only complication is how to find change in potential energy because we do not know how much are the particles moving in the vertical direction. Now for that, we do something like this. We say, if A is moving x meters downwards, then B is moving x meters in this direction. Now for B, what we can do is we can make a right angle triangle like this. So I've made that bigger on the right side. We know this side is x. We know this angle is 30 degrees. right? Corresponding angles. And now, if this total distance was 1 meter, A is going down by X. When they come at the same horizontal level, how much has B moved up by? 1 minus X. So the vertical height, change in vertical height for B, that is going to be 1 minus X. So in that triangle now, we can say this side is 1 minus X, this is X. And we can find the value of X from this, use sine, and that gives you X equals 2/3. So now we know exactly how much vertical height is changing for both of them. The value for X is 2/3. So this is 2/3, and this is 1/3. 1 minus X, that will become 1/3 then. So we know that A is going down by 2/3, and B is going up by 1/3. And now using that, we can find the change in potential energy. How do you do that? Work done by driving force, there's no driving force here. So we ignore that. Change in kinetic energy. Now, speeds are going to be common between them, right? Whatever speed A is moving at, B is also connected to that. B is also moving at the same speed. So we can consider that together for both of them. If you want, you can also do it separately. You could also do half into 4 into v² minus 0² for A, and then half into 3 into v² minus 0² for B separately. That will work. But since the speeds are common between them, we could just combine them like this in one expression. The total mass is 4 plus 3 into v² minus u² divided by 2. That's the change in kinetic energy. But potential energy cannot be calculated together because the changes in height are different for both the particles, right? Changes in height are different. A is moving down by 2/3 and B is moving up by 1/3. We have to calculate the change in potential energy separately for both of them. Now for A, how do you do that? mg into change in height. Mass is 4. G is 10 into change in height. Height is decreasing by 2/3. So we put a negative value here. When it's a decrease, we put a negative value. You can either put a negative value with the height there so that the overall number becomes negative, or just directly put negative value here because it's a decrease in potential energy for A. For B, we can say it's mass of B into 10 into change in height, that's 1/3. And then you just solve this equation, find the value for B. It's a 6-mark question. Again, it's more for the thinking involved in this. The actual calculation is not that much. That's the value that you get from this. Why are we considering it? Why would we not consider it? Both particles are moving, right? The overall for the whole system, we know that the driving force, work done by driving force, is supposed to be equal to change in kinetic energy plus change in potential energy plus work done against resistance. We have to consider everything in the system, right? Let's consider this example. Again, it's about change in vertical height. They're saying two particles P and Q of masses 2.5 kilograms and 0.5 kilograms. They are connected by a light string. P is 2 meters above the level of Q like this. Vertical distance between them is 2 meters. And again, what they're saying is, find the acceleration of P first of all. When P is released from rest, the string taut, the pin is rough, with the coefficient of friction this. You just represent all the forces, apply Newton's second law of motion on both the objects, you find the acceleration. From that, the first part is pretty straightforward. Simple application of Newton's second law of motion. But now in the second part, it says, use an energy method to find the speed of the particles at the instant when they are at the same vertical height. Again, we think of it the same way as before. P moves down the plane, Q moves up the plane. If Q moves up by x units, P moves down by x units, right? For P, then, we can make a right angle triangle like this. In that right angle triangle, we can say, if this is x, then the remaining part, this part, that's going to be 2 minus x. So we have this right angle triangle with perpendicular is 2 minus x, hypotenuse is x, sine 30 equals this. Find the value of x from that, and you get 4/3. That means the change in height for Q is 4/3. If that's 4/3, what's the remaining change in height for P? That's 2/3. And again, height for P is decreasing. So we put negative with that in this equation. Height for Q is increasing, we put positive with that. It's a smooth surface, so there's no resistance, and there's no driving force because there's no force acting apart from weight in the forward direction as well. Solve this equation, find the value of V. Again, 5 marks. This is what you have to do. Exactly the same question. These are both from recent papers. You need to make sure that you understand this well. Yes, in this case, you could use conservation of energy as well because there's no driving force, there's no resistance. Conservation of energy would also work. Yes, that's correct. You could use that. That will work in this case because there's no driving force and there's no resistance. All right. I hope that was helpful. We stop at this point. If you have any questions, you can let me know.